All right, so let's look at this example. Let's pretend that you can push 500 newtons horizontally. That's the maximum you can push. You know that from the gym or something. And, that's like 1,000 pounds. And you can barely push a refrigerator that has a weight of 1,500 newtons. You want to find the coefficient of static friction between, actually, that's 250 pounds. No, that's 500 pounds. 500 pounds, or about 1,000 pounds, 1,100 pounds. All right, so we want to find the coefficient of static friction. All right, and how do we do this? Well, we're going to have to find what's happening with all these forces. The only force here that is not a reaction force, I think, is the weight. Well, I guess you've also got another one, which is your push. That's not, I guess that in a way is a reaction force, but we're given the number for that. So we'll put a push over there, and X and Y. But the refrigerator, if you draw a refrigerator with a U pushing it, the refrigerator has a weight coming down, so the universe pushes up on it, or the floor, not the universe, the floor pushes up on it, and then you're trying to push this way, and the friction is not letting you do it, so it has to push the opposite direction, here, F. Okay, so those are our, that's how we figure out what's going on. We sort of draw a picture and say, okay, well, what's happening? All right, so then we have these forces, right? The push and the normal force and the frictional force and the weight. So we add these up, right? Just vectorially, like we said in the first part of the lecture. So we have our normal force coming up here, we have our push here, and straight down is our weight, and over here is our frictional force. That comes to 0 because it's balanced. All right, so pretty good with that. Now what we'd like to do is we'd like to take this picture and find the x and the y directions, right? So in the x direction we have the push to the right and the frictional force to the left, P minus F equals 0. The y direction we have the normal force coming up and the weight coming down, that's N minus W is equal to 0. Okay. What we really want to find is the coefficient of static friction. This is something that has to do with this guy, so we want P minus mu n is equal to 0. The way of saying that is mu n is equal to P, or something like that. So we want this, but we don't know that normal force. And the only way to get it, because a normal force is also a reaction force, is to use this free body diagram, this force diagram, Newton's first law, that says that the weight and the normal force balance out. That's perfectly useful, right? That means N minus 1,500 newtons is equal to 0. And if we add 1,500 newtons to both sides, you have 1,500 newtons. N is 1,500 newtons. We're doing pretty good, right? So we can then plug this back in. So mu times 1,500 newtons is equal to our push, which was 500 newtons. So mu is equal to 500 newtons over 1,500 newtons. We divide by 1,500 newtons. That 5 goes into 15 3 times. Cancel all those zeros. We have 1/3. Our coefficient of static friction is 1/3. Okay, so for this, the difference between this and the first example is that both directions were very, very important to solving it. That's because the friction, which was, we're just barely able to push it, so that means our friction is at its maximum, which is mu Sn. That friction is proportional to the normal force, and the normal force is perpendicular to the friction. because of that, we have to solve both situations just to find that normal force. We want to find that normal force, so we have to do both the x direction and the y direction. We have to find the y direction to find the x direction. And once we've done the little bit of math to find that, we can plug that back in and use the other information to get a situation where we can just divide once and find the coefficient of static friction. So that's more or less how this sort of problem works out. All right, bye now.